In this video, we're going to be looking at the counterpart to empirical formulas called molecular formulas. So while an empirical formula is the chemical formula of a compound that is expressed in lowest terms, molecular formulas are chemical formulas when they are not expressed in lowest terms, and there are a few examples below that we can look at in order to distinguish the difference. For example, with P4O10, we see that they have a common factor of 2. The number of phosphorus atoms divided by 2, 4 divided by 2 is 2. And if we take the number of oxygen atoms, 10 divided by the greatest common factor 2 is 5. So here we see that 2 and 5 do not have a common factor other than 1. Therefore, this is our empirical formula, and the molecular formula, P4O10, is not expressed in lowest terms. We can do the same with most of the other formulas below. For example, C10H22, again, has a common factor of 2. If we divide the number of carbon and hydrogen atoms by the greatest common factor 2, we would get C5H11. Again, this is an empirical formula because 5 and 11 do not have a common factor other than 1. With C6H18O3, we see that these have a common factor of 3. 6 divided by 3 is 2. 18 divided by 3 is 9. And 3 divided by 3 is 1. So again, 2, 9, and 1 do not have a common factor other than 1, so this is our empirical formula. Here, we see C5H12O. This is not actually a molecular formula at all because 5, 12, and 1 do not have a common factor other than 1, meaning that this is actually an empirical formula. Finally, an easy example, N2O4. 2 and 4 have a common factor of 2, so if we divide the number of nitrogen and oxygen atoms by 2, we get NO2, which is our empirical formula. So, now that you understand the distinction between molecular formulas and empirical formulas, it's time to look at what these look like in calculations. So whenever we are dealing with a molecular formula, part 1 of the question will always involve finding the empirical formula first. So this is a fairly standard percent composition calculation here. We know that, again, the sum of all percent compositions is going to be 100. We can't use percentages, so let's use the cheat. Let's cross out these percentages and say that we're dealing with a 100-gram sample such that each of these percent compositions would correspond to the same number in grams. Again, we can't compare masses directly with each other because carbon, hydrogen, and oxygen have different molar masses. So let's convert the mass numbers into moles, starting with carbon. We start with 52.65 grams of carbon, and we remember our molar mass of carbon because we've done it so often already. If we want to cancel grams and convert to moles, we multiply our mass of carbon by 1 mole over the molar mass of carbon, which is 12.01 grams. If you put this into your calculator, this comes to approximately 4.384 moles of carbon. Again, significant digits not relevant here because we're looking for a formula in the end. Let's do the same thing with hydrogen. So we start with 5.27 grams of hydrogen, and we're going to multiply by 1 mole over the molar mass, 1.01 grams. And if you put this into your calculator, this comes to approximately 5.218 moles of hydrogen. Again, significant digits not important. Finally, let's do the oxygen calculation. 42.08 grams of oxygen multiplied by 1 mole over the molar mass of oxygen, which is 16.00 grams per mole. Grams cancel, and if you put this into your calculator, this comes to exactly 2.63 moles of oxygen. Again, these mole numbers aren't actually useful on their own. We need to compare them to each other. So let's look at the smallest mole number and use that as our benchmark, which is oxygen. So again, if we take the moles of oxygen and divide that number by itself, I don't need to bother with the calculation because any number divided by itself is always going to be 1, and therefore that is our benchmark. So if we assume that we have 1 mole of oxygen, how much carbon and how much hydrogen are we going to have? Let's do that calculation now. So let's start by checking our moles of carbon over our moles of oxygen to find the ratio between the two, and that's equal to approximately 4.384 moles of carbon divided by 2.63 moles of oxygen. If you put this into your calculator, this number comes out to approximately 1.666, and there's a bunch of other decimals after this. Again, this is not a number that we can easily round up or down because it's not 1.9 or 1.1, so let's just hold on to this until we figure out hydrogen. Next, let's do our moles of hydrogen divided by moles of oxygen, which is, again, approximately 5.218 moles of hydrogen divided by 2.63 moles of oxygen. If you put this into your calculator, this number comes to approximately 1.984. 1.98 we can safely round up to 2. So what this is telling us is that for every 1 oxygen that we have in the formula, we need approximately 2 hydrogens and 1.66 carbons. Well, we know it's impossible to have 1 2/3 of an atom. So what can we do to keep these ratios, the ratio of oxygen to hydrogen to carbon, the same, and to get this as a whole number? Well, we know whenever we have certain decimal numbers like this, we can take the whole empirical formula and multiply it in order to get this to a whole number. So if we multiply this by 3, 1.66 times 3 is actually 5. And then 3 times 2 is 6, and 3 times 1 is 3. And we see that this empirical formula works because 5, 6, and 3 do not have a common factor other than 1. So we have successfully found our empirical formula. Where the molecular formula comes into play is if we are told that this unknown compound that we want, we have actually been able to figure out what the molar mass of that compound is, what is the molecular formula, what is the formula of this compound not expressed in lowest terms. So in order to do that, the first thing we would need to calculate is the molar mass of our empirical formula. So let's determine that first. So we know the molar mass of carbon is 12.01, and our empirical formula has 5 carbon atoms. So 12.01 times 5 comes out to 60.06. Let's do the same thing with hydrogen, 1.01, and our compound has 6 hydrogens, which comes to 6.06. And then if we do the same thing with oxygen, 16.00 times 3 oxygens, and that comes to 48. And if we do some quick arithmetic here, I realize that I made an arithmetic error. 12.01 times 5 is 60.5. Make sure that you're careful with your arithmetic as I'm doing here. And if your arithmetic is correct, we have found that our empirical formula's molar mass is 114.11 grams per mole. Now, in order to figure out what our molecular formula is, we need to compare the molar mass of the molecular formula. So I'll just write that out. Our molar mass of our molecular formula, which is 343 grams per mole, and we're going to compare that to our empirical formula. So divide by the molar mass of the empirical formula. And if we do that right here, what we're going to see is how much larger our molecular formula is compared to the empirical formula. So if we divide 343 grams per mole by the molar mass of our empirical formula, 114.11 grams per mole. If you put this into your calculator, this number comes to approximately 2.98, which we can safely round up to 3. So what this tells us is that our empirical formula, if we multiply our empirical formula by 3, we would get the molecular formula. Well, if that applies to mass, it also applies to the compound itself. So if we take this number, this factor that we have here, and multiply our empirical formula, C5H6O3, by that formula, we should get our molecular formula. So if we do that, 3 times 5 is 15, 3 times 6 is 18, and 3 times 3 is 9. We have just found our molecular formula. So in summary, once again, once we have found our empirical formula, we compare the molar mass of our empirical formula to the molar mass of the molecular formula to find how much bigger our molecular formula is from the empirical formula. Once we find that out, simply take that factor and multiply it by the empirical formula in order to find what the molecular formula is.